Okay, propellers. You've got to match the propeller to your motor to get the most performance. So the propeller, the speed controller, the motor are all matched together. When you buy a motor, it'll tell you what kind of propeller to buy for that particular motor, and it's wise to follow their guidelines. You can see the propellers have got a diameter and they've got a pitch, which is the angle of the blade. Notice the propeller has got less pitch on the tip, more pitch at the root, because the tip is travelling faster. You get more lift there. If you had more pitch there, it would bog down. You'd be getting too much lift there. This evens it out. Three-bladed propeller. You've got the numbering there. And a big two-bladed propeller. These are off big internal combustion motors. Okay. So the numbering, this one here, you probably can't see, but it says 25.4 by 11.4 millimeters. So that's diameter, 254 mil diameter by 114 pitch millimeters. So that's the first number is diameter of the motor, and the other one's the pitch. Now the pitch is the angle of the blade. And this one, 20 inches by 10 inches pitch, 20 inch diameter, okay, which would be from the arc in the center, by 10 inches pitch. So that is easy. It's the pitch that's the interesting part. It just means with every one revolution of this propeller, it would move 10 inches forward. So you can take your students through what it means to have fine pitch propellers and coarse pitch propellers, but that's just the numbering. Okay, so that's a big aeroplane motor, model aeroplane with a large 50 cc motor in it, and these are drone. Okay, that's metric there. It's also got metric there. Sorry, and it's got imperial here. So it's got 10 inches by 4.5, so 10 inches long by 4.5 inches pitch. So 10 inches is diameter, and the 4.5 inches is every one revolution it would go 4.5 inches forward. The lower, that second number is really quite important. The lower that second number, the more torque it has, more power, like a takeoff, but less top end speed. The higher that number, if that went up to like 10 by 8 or 10 by 10, that's a higher speed prop. Because these are fixed pitch, the pitch doesn't change during flight, unlike full-size aviation. But you have to really work out what sort of performance do you want. Do I have high-speed flight? I'd have a big second number. Okay? And you can talk to your students about what happens with relative wind as this propeller is moving forward. Instead of the wind hitting it that way, now, because I'm moving forward, the relative wind is coming this way because it's generating its own wind as it's going forward, as well as rotating, which means the pitch of this blade is being reduced. All right? And if I want to go faster, all I'm doing is reducing the pitch because of that relative wind. So really, if I really want to fly fast, I have to have a lot more pitch on to compensate for that. But you can talk to your students about relative wind and propellers. A fine pitch, like a lower second number, means that I'm static, I'm not moving forward, I throttle up, the wind is in this direction. With a fine pitch, there'll be less load on the blade, so this can actually rotate faster without loading up, and I'll have more instant performance. Whereas if I had quite a coarse pitch and I'm standing still, as I throttle up, that coarse pitch would be slapping the air like that, slowing the blade down, and you'd have a reduction in RPM. So fine pitch for torquey kind of things like takeoff, power, hanging on your tail, just hanging there like that. And as I go faster, you want the pitch to increase, which I can't do on this obviously, but it'd be great if I could, so that the relative wind, which wants to reduce my pitch, is not affecting me as much. Okay, propellers. For your drone also, most drones will be we'll rotate this way, front two, so like that, and diagonals go the same way. Diagonals go the same way. Now that's, most drones are like that, and you'll configure that in your software. Front two like that. I say it's like a crab feeding itself. They rotate like that. Diagonals go that way, diagonals go that way. And you need to check that. If you throttle up your drone and it flips over, probably you've got the wrong props on, you've got them swapped over. And as you know, for your drone, you probably realise this, there's my quad rotor, that's the front. If I want to pitch forward, I command that on my controller, the back two motors will throttle up, pitching it forward. If I want to pitch back, same. If I want to roll left, the two right hand motors will throttle up. If I want to roll right, the two left hand motors. The question is, if I want to yaw, how does the system accommodate that? Stop the video now so you can have a think, because this is the whole beauty of Newton's third law. Okay, so I want to yaw left, okay, because Newton's third law, each and every action is an equal and opposite reaction. Okay, natural tendency of rotational things, if it's rotating this way, the thing that's attached to you wants to rotate the opposite way. So if I want to yaw left, these ones are spinning this way, the tendency is, so they're going clockwise, the tendency is for the aircraft to want to go left. So if I throttle those up, there'll be a natural torque reaction of the airframe to go left. If I want to go right, I throttle these ones up, they're going anti-clockwise. And if I increase the throttle on those, if I yaw right, my left gimbal, they'll throttle up and the thing will want to yaw right. They'll throttle back a bit. Okay, and these ones will speed up, thus causing a torque reaction round to the right. Okay, propellers 101.